Okay, just to warn you, we're going to go over some really heavy stuff today, but I'm going to make it as light as possible and work through it step by step. This is the video I wish I had that would have saved me months of work, because today we're going to talk about ARMA, AutoRegressive Moving Average Model. You already know what AutoRegressive means because we've covered it in the last video in the series. So we're basically looking at trying to model some kind of asset's behavior based on the prior time period, or prior time periods if you're using more than one. But then there's this MA part, which is moving average. And you're probably thinking of moving averages where you just average something by, say, 12 lags or 12 periods or whatever number you want to use over time. This is nothing like that. This has nothing to do with that. So just throw that out your mind for now. We're not talking about moving averages here. This is very, very different. One other thing we're going to be covering here is maximum likelihood estimation, which actually is really, really interesting in and of itself. And it is the heavy part of all of this. I never really understood it when I first started using it, and I was using it with code, or I was, building workbooks with formulas that already existed. But understanding this really helped me with a lot of the things that I wanted to build and develop later on. To understand ARMA, let's just jump back to the AR part first again, the auto-regressive moving average. Remember, if we wanted to model XEC USDT, we'll stick with that asset for now, and let's just call that X, just to save us writing that out too much in this video. We can say X sub t is equal to alpha plus some coefficient beta times the previous time step, so X sub t minus 1, plus some market random shock or error or residual, whatever you want to call it, which we'll give the name epsilon here, or the symbol epsilon sub t. So just to recap what this means, we are saying here that we're trying to model an asset to say that we can predict what the returns of XEC USDT will be, in this case, based on some constant value, plus a proportion of its prior returns. And then there'll be some error involved in that, which should follow what we call a normal distribution if we were to look at all of them. So that's what this formula is saying. But now we don't just have to model this based on its prior lag. We can also model it based on its market shocks, or these very residuals. And in which case we could say that X sub t is equal to alpha, some constant, plus some coefficient. I won't call it beta now. We'll leave that for the AR model. Let's give it a different name. I'll call it phi. And that will be a proportion of the prior period's market shock, so epsilon sub t minus 1. And so that will be our new forecasting process, plus there'll be some new epsilon sub t, because we'll have, market shocks or errors from our predicted value versus what actually happened. This is called an MA, or a moving average model, and this is of order 1. So it's an MA1 process that we're modeling here. And we can actually combine these two things together as well. We could say that we want to build an ARMA model, which would be X sub t is equal to alpha plus beta X sub t minus 1 plus phi, which is of the prior period's market shock, so epsilon sub t minus 1, plus some epsilon sub t. Here we have our AR process, and over here we have our MA part of the process. And this alpha and epsilon term, they're just the same. I also don't have to model this just based upon a lag of 1 for each of these. I can mix those lags up. I can put more lags in if I want to. So I could say, for example, X sub t is equal to alpha plus beta sub 1 of X sub t minus 1, so the prior time step, plus beta sub 2 of X sub t minus 2, 2 time steps. So this would be a lag of 2 for the AR process. And I could do the same for the MA part of this. So I could say plus phi sub 1 of epsilon t minus 1, and then plus phi sub 2 of epsilon sub t minus 2, and then plus some error term. And here I've actually got an ARMA process of 2, 2 rather than 1, 1. But I could have 3, 4, or whatever combination of these that I believe I can model this process on, these returns for XEC USDT. We could also simplify how we write this just to help you with some math notation. Let's just call the lags of the AR process P and the lags of the MA process Q. This is just standard, and that's what I'm going to use. So I could say here X sub t is equal to alpha plus the sum of these two terms plus the sum of these two terms over here. And we'd write that out as sigma with a p on top, because I want to do it for the number of p items, where starting with p equals 1, of beta sub p of x sub t minus p. So that takes care of writing out the terms here for the AR process. So you can see here, if I had like 10 lags, it would save me writing out xt sub whatever 10 times. Great. And then plus the same again here for the lags with the market shock. So the MA process, except here, instead of using beta, I'm using phi. And on top of the sum or the sigma here, I'm using q instead of p. And also here, t at sub t minus q. So this is exactly the same thing. The only difference now is it's written in a way where it saves me having to write out the terms the same multiple times. Just to pause here for a minute, if you've heard of an ARMA process, so ARIMA, the I stands for integrated. And we'll talk about that a little bit later when we get into stationarity and co-integration and things like that. But it's very straightforward. It just means differencing whatever data I've got here until that data becomes basically stationary. Meaning, I'll just give you a very high level overview of what that means very quickly. It means that if I look at the data in any time order whatsoever, that the mean, the variance, and the auto covariance of that data that I'm looking at is going to be constant, no matter how I mix up that time. And so the I just means how many times I had to difference my data for it to become stationary. And we would say then that data is integrated of order, say 2, if I had to difference it twice. And so an ARMA model would become an ARIMA model, and that I would be represented by a D. Instead of just P and Q, we would have P, Q, and D for the amount of differencing required. So that's all that ARIMA is versus ARMA. I don't want to get hung up on it, and I certainly don't want to make this video about that, because stationarity is going to become a lot more important in subsequent videos. I don't want to focus on it too much here. So let's just take a step back and think about how are we even going to estimate these parameters. So if we look at our AR model first, we can see here that I could just take x sub t minus 1 and put that into an OLS process. The same with our constant. By the way, I never showed you before how the constant is actually estimated, but it's just by putting in another independent variable, which is just a column of ones. So there's no data involved. It's just a data column of ones. You don't have to fetch data from anywhere. We just put 1. So we're feeding this column of ones and this column of x sub t minus 1 into our OLS process, and then we're able to forecast x sub t as an estimate with our little caret on top, and the same with our alpha and beta. So using ordinary least squares, we can make those estimations. But now when we look at the MA process, let me ask you, where are you going to get your epsilon sub t minus 1? Because isn't that calculated as a byproduct of the estimate we just did? It's, in fact, when I try to get my own head around it, even now talking about it, you can see my brain is sort of trying to work recursively. You sort of get stuck here. So that just means that there's going to be some kind of recursive process to trying to figure out and estimate what these parameters are, especially this phi parameter. Also, in order to perform OLS, there are some key assumptions that are made. Number one is that the errors are independent. There's no autocorrelation on the residuals or the errors. And this is by the very nature of the MA process violated, because we are using the errors themselves and saying there's a proportion of the prior error that's involved in the new number. So there's kind of a violation of that right there. And so we're going to need to use a different estimation method here, in which case Q, maximum likelihood estimation. Now, to understand maximum likelihood estimation, I'm first going to just start with a probability distribution, because this is absolutely fundamental to everything we're doing here. We're going to build together our own normal distribution here. So I'm going to call X, and this could be X at any times T. I'm just going to make up some numbers here. I'm going to put -5, -4.9, and then I'm just going to drag this down all the way until I get to +5. So let's see, when do I get to +5? 6.4. There you go. Let's just format this so it all looks nice and neat. By now you're used to what I'm like. Now what I want to do is build some kind of probability distribution for you. Now, to build a normal distribution, we're going to use this formula over here. So this is the Gaussian standard normal bell curve distribution that you've probably heard about before. And it takes two parameters. You can see here, or at least it takes the value of whatever x is at time t, or x sub t. And then it takes two parameters here that are fixed. So one is going to be mu, which basically means the mean or average when we're talking about a sample of data like we are here. So you could almost look at that as saying x bar. And then the variance, which is sigma squared, which, as we learned about when you're dealing with a sample of data, is also known as s squared. But here we're dealing with an entire population and a formula over here. So we're going to talk about mu and the variance, or sigma squared, because this is how you're going to see it written absolutely everywhere. And so here, this is going to be our probability density function. Now I'm going to build it and then graph it for you so you can see that this is in fact a bell curve. And then we're going to use this formula to help with explaining maximum likelihood estimation. So here I can just say this is equal to 1 divided by the square root of 2 times pi times the variance. Now I don't have a cell for variance, so I'm just going to link that over here and close that formula for now. I'm going to come back to it. So let's actually just put a variance in here, and I'm just going to call this s squared for now, because you know what that is. It's the variance, it's sigma squared. And I'm just going to put a number in here for now. I'm going to put a number of, let's say 1. So 1.0 is fine for the time being. So there you go. I've now got my variance, and I'm also going to need mu as well. So let's copy this and put that there. And here I'm just going to put u to represent mu. Or in fact, one thing we can do is we can use this symbol over here. So format this as symbol and put m for mu. And then you can see here, it formats mu for us. Brilliant. And I'll give that a mean of 0. So we have a mean of 0 and a variance here of 1. And this is known as a standard normal distribution if you have 0 for the mean and 1 for the variance. And that's what we'll build out for now. So we're going to take that number multiplied by the exponent of, and then it's going to be minus. And here I'm going to have x, which is right now at this data point is minus 5, minus mu, like such, divided by 2 times this number over here, this variance. And we need to put that in brackets as well. Things can go very wrong very quickly, especially when working in Excel, if you don't get your brackets right, by the way. So we've got that number over there, and that's then going to be squared, and close that bracket over here. So it's going to be x minus mu, and also that needs to be squared, divided by 2 times the variance, also squared there, and close our final bracket and enter. Brilliant. Let's drop that down. Now, just to test that I've got that right in Excel, let's just say this is equal to norm, norm.dist, there you go. And here's our x value, here's our mean. And now instead of for the variance, it's actually asking for standard deviation, which is just the square root of the variance, which we've covered in prior videos. So this is not new stuff here in terms of, for those of you who have been following the series, this is just the square root of the variance, which is the standard deviation squared. And then it's asking, do I want cumulative distribution or non-cumulative? What it's saying is, do I want the density function, which is not cumulative, or the cumulative version, which is known as the distribution? Well, I want the density function. So here I'm just going to put 0 for false. And here Excel gives me this number. I'm going to drop that down, and then I'm going to copy this formatting over here. Now, this was a good check because I got something in my formula wrong. Look here, I've squared this, where this is already s squared. It's already squared. I shouldn't be squaring that number twice. And even if I was supposed to, I'll put it in the wrong place. So that's fine. There we go. So this is then going to be divided by 2, multiply that number there. And there we go. Now I get the same result. So here we are. That's the formula that we should be using in order to type this out correctly. Right, let's just format that here. And there you go. You can see these numbers match exactly the same. Now let's just delete that x so that Excel can tell that this is going to be the x-axis. And I'm going to highlight all of this data like follows. And I'm going to insert here a line graph. And brilliant. There it is. Now let's move that here up to the top of our spreadsheet. And there you go. You can see our standard normal distribution, our bell curve, with a mean of 0 and a standard deviation of 1. So we'll fix this here between 0 and let's just say 0.5. Now I'm just going to highlight these cells here in yellow to show that these are the ones that I'm going to be playing with and changing. And there we go. So let's say I want to change my standard deviation to something like 2. Well, I do that. You can see that this normal distribution is now spread out. It's a lot wider. The variance is wider. It covers more range. but the probability is also being spread out more wide. So here in the center, it's not as high. What if I put this back to 1 and I change the mean? Instead of it being here at 0, I put it at 2. Well, you can see I've just moved that probability distribution over there. Let's go and increase the variance as well. So now you can see I've not only shifted my probability distribution to the right, I've also spread it out quite a lot too. So the center of it, where it's centered, has now shifted from here to here, and it's also spread out more wide. So that's quite interesting. So let's move that around. Let's move this to -1. And now you can see that it's shifted here. The center of our distribution is actually here at -1. Now, why am I showing you all of this? Well, remember our moving average process that we wanted to estimate using maximum likelihood estimation. We had x sub t is equal to alpha plus phi times the prior period's shock plus some other current market shock or residual value. And we now want to go and model this. So let's go and draw a graph now and put all of our data points. Let's say all of these data points for XEC USDT, all the returns, we're just going to go and plot them here on the bottom and call those X. So here I've got my X axis, and here I've got my data points representing the values from the sample that I've actually detected. And now I'm going to try to draw, using my eye, a bell curve, a distribution that looks like it would fit that data quite well. And so I might draw something like this over here and connect it to these data points. You can see here that where most of the data points are clumped together, that's also where the highest probability of finding that data point exists. All we're doing is fitting a curve to that data. I could have also drawn a normal probability distribution like this, and I'll connect it to the same data points. And so you can naturally see that the curve is not very well aligned with our data points. So it's not been fit very well. Now, it's fine to do all of this by eye, but surely there must be some kind of numerical approach we can use to know exactly what distribution should be fit to this data so that we know it's been perfectly fit or is as well fit as we possibly can do it without just relying on our eye. One way we can do that is to assume that each of these data points that we've marked here on X are completely independent from one another. In other words, one does not influence the other. We're just going to make that assumption for now. And we know from probability theory that if we want to know the probability of all of these occurring, or let's just say 2 of these occurring. So in other words, if we want to know the probability of A and the probability of B, then we can just take the probability of A and multiply it by the probability of B. In other words, I can just multiply all the probabilities I get from this distribution here. I could multiply every single one of those together, and that would give me a sum total of the probability of all of these occurring together. And the curve that gives me the highest probability of all of them occurring together is going to be the best fit curve. So if I multiplied this value by this value, by this value, by this value, by this value, so on, let's just say I get a number of, 125. And then here, if I take this curve and do the same thing, I multiply all these together, and I get a number of 95. Well, I know that that curve's not fit quite as well. Multiplying all these numbers can actually be a bit of a pain. In fact, it would be a lot easier just to be able to sum numbers than multiply them. And luckily in math, there is a trick to doing that. Let me give you an example. Let's say I have a number which is 10 and another number which is 5. Multiplying 10 by 5 gives me, as you know, 50. Now, watch what happens here. If I take the natural logarithm, so if I just take the log here of 10 and the log of 5, and then I sum those two up there, and then to get back to a number that's not log, I can just take the exponent of that number. You'll see here I get back to 50. So by taking the logarithm of something, I'm able to sum these probabilities rather than having to multiply them. So let's take a step back. If I fit a probability curve to this data, I'm basically trying to work out what is the likelihood of this data having ended up the way it did. And so I need a likelihood function. So I'm going to just denote that with a capital L. And this function's going to take in some parameters. Let's just call those parameters theta for now. This just means a whole bunch of parameters. I'm not going to define them right now, but we have this function, and that's our likelihood function, and that's just going to be the multiplication. So here I'm going to use this giant pi-looking symbol over here to resemble multiplication iteratively of whatever our distribution, or I should say density function is here that we want to use to represent this data. And here we're basing it on a normal distribution. So I'm just going to write that here as f of x for now. Don't worry about what I just said there too much, because I'm actually going to dissect this in detail for you. But that's what we're mathematically describing, what we just said we wanted to do graphically. We basically want to multiply all these things together to come up with this likelihood number. But if I take the logarithm of this likelihood number, then I don't have to multiply those probabilities together. I can just sum them. And that will give me the log likelihood. And that's still absolutely fine. I can use either one to get a curve properly fit. It's just much easier to use the log likelihood when we actually come to model this. That's a lot. Let's just take a moment to pause here for a second. What are we doing? We're trying to find a distribution curve that is going to best fit our data. The reason we're doing that is because it's going to give us a number at the end of that. When we sum up all the probabilities of that data being where it was, it's going to give us a number. And at first, that number is going to be completely incorrect because our curve is not going to be even fit. We're going to randomly choose some parameters for our model, and it's going to be garbage. It's not going to make any sense. But then what we're going to do after that, and this is the point that I need to make now, and I'm going to make it again later on just to tie this all back together. We're going to use sheer computing power to figure out what the optimum parameters are so that that curve gives us the highest number possible. Because remember, if we get the highest number possible, we know that we've got the best fit of that curve, and therefore we've likely got the best parameters as part of our model. So that's what we're actually putting together over here. And so this x sub t, which is going to be equal to our alpha plus phi of the prior period's market shock plus the current market shock or error, whatever you want to call it, is really given by this maximum likelihood. Let's actually start modeling this now. I'm going to call this sheet ndist or something like that and move on to a new sheet. And let's just get some data. I'm going to zoom in here for you as well. Let's just get some data put together over here. So here I've got a data tab, which is my XCC USDT. I'm just going to go and link to those returns very quickly over here. And there we go. I've got my returns data. So looking at our formula for the MA process, I know that I need to forecast alpha and also phi. So I'm going to go back over here to my normal distribution. I'm going to copy these across here. And I'm going to put A for alpha and F for phi over here. So in fact, let me just copy that, A and F. There you go, alpha and phi. And I'm just going to put this to 0.1 and this one here to 0.1 as well. Now I also need a column for epsilon, and I'm going to assume at the first time step there was no error because time has just begun at this time step. So there will be no error here. But then what do I put in for all these errors over here? Well, I need to first then create some kind of forecast to calculate what the errors are. So I could say here, let's just call this X hat or Y hat or whatever we want to call it. We were using X in our math notation, so maybe I'll just call that X hat over here. I think in another model I've used Y, but that's fine. We're going to make our predictive column of data. And so that there is very simply going to be alpha plus our phi number. So this proportion of our prior ET minus 1. So epsilon at t times minus 1. That is our MA formula. Remember, it's alpha plus phi times epsilon at t minus 1. And that's going to give me this X hat or Y hat, depending on how you're calling it. And then my epsilon is going to be equal to what actually happened versus what I predicted. And there you go. Now I've got this epsilon. And you can see here that this is now just giving me garbage, actually, more than anything. It's giving me this number that I know is wrong because I've just made these numbers up. They don't actually mean anything. But at least I'm starting to build an idea of what it is I'm trying to do up. I've got this X hat and I've got this epsilon and the prior time step, which is epsilon t minus 1. In fact, if I wanted to, I could write this as t minus 1 over here, just if you wanted that separated as its own variable, just like we did in the formula. And if epsilon there is 0, then this number here would be that one, and so on and so forth. And so this here wouldn't be multiplied by that. it would be multiplied by this column here. So it's exactly the same calculation. There's no change to the numbers whatsoever. It's just a display thing. You might prefer it displayed out like you've actually written the math formula. So there we go. I have some constant here plus phi times epsilon at t minus 1, and then plus some error. And that gets me back to this number over here. So what do I need? I need some likelihood function, which we're going to call the log likelihood. I need some likelihood function here, so some number that I can maximize, that when I maximize it by tweaking these parameters here, and this gives me the maximum number possible, that I know I've got the best fit for a distribution on this data. And I don't need that distribution, by the way. I can throw the distribution away. I don't need it. I'm using it as a way to derive this proportion of this value here plus some constant. So I need some kind of formula that I can put in here that's going to fit a distribution, give me one number out, and then I can tweak and change these until that number is the highest number possible. And don't worry, I'm not going to tweak and change these manually. We're going to use computing power to do that. So what distribution should we actually fit to this data in order to do that? Well, let's just use the normal distribution. And so here, that is given by, as we saw over here on the endist tab, that is given by 1 over the square root of 2 pi times the variance times the exponent of negative x minus mu squared over 2 times the variance. Okay, that's the formula we're going to be working with here. So if it looks daunting to you, don't worry about it. It should if it's the first time you've seen it. And so this will give us a function of x given some fixed parameters, which are mu and our variance over here as well. So that mu and variance won't change. They're just going to be fixed, meaning that in our model here in Excel, we're actually going to need a parameter, which we're going to call mu. And so that's something we're going to need. And we're also going to need a parameter. So I'm going to move this down, which is our s squared. So it's sigma squared. So we're going to need that as well. And we should call that s squared because here I'm really working with a sample, but it's fine. We're going to call this sigma squared and mu rather than x bar and s squared over here. It's the same kind of idea. This is the first central moment. This is like, think of it like the average. And then this over here is our variance. And so we could actually write this as x sub t follows, and this squiggly sign means follows, a normal distribution, so capital N, and that normal distribution has parameters mu and the variance, which we've just discussed. So that saves me writing out the whole normal distribution again. And one thing you should note here is that we have this constant value, which is mu. And I've kind of put it up here twice. I don't want two constants. I've already got my mu constant. In fact, these two here, alpha and mu, they are one in the same thing. And so here I'm just going to rename alpha to mu. And so I could write that as my normal distribution as follows, is x sub t given the prior time period residual, so epsilon sub t minus 1, follows a normal distribution with parameters mu plus phi times epsilon sub t minus 1 and the variance. So now I've got my three parameters. I've got my mu, I've got my phi, and I've got my variance over here as well. And then what I can do is take my normal distribution formula and I could substitute this mu with minus mu in brackets plus phi times epsilon sub t minus 1. Or another way to write that would be minus mu minus phi times epsilon sub t minus 1. And so this is now a function of xt given epsilon sub t minus 1, which is dependent upon some parameters. We have x sub t is equal to mu plus phi times epsilon sub t minus 1 plus epsilon sub t. Okay, we know that is the formula that we're trying to model. Well, when we're at the first time step, what is epsilon sub t minus 1? Well, we said before, we're just going to make it 0. And so anything times 0, phi just becomes irrelevant as well. So we can just put a 0 here, plus epsilon sub t is equal to 1. So this is epsilon at time t is equal to 1. That's what that would equal, because as we had also seen in Excel, it's just a 0. We can see it here. This is 0. So it's just going, this is just going to be equal to phi times this number, which is just 0. That's all this is, plus some error term over here, which is what this is at t equals 1. So this has now become our t equals 1. What that also means is that epsilon at t equals 1 is then just x at t equals 1 minus mu. So literally, if I just take this number here minus mu, I get back to this number here. Let's take a step forward to this next time step over here. We can say that when x sub t equals 2, so we're at time step 2, that is equal to mu plus phi times epsilon sub t minus 1 plus epsilon at time t, which t is equal to 2. And we could write that another way, where here we could write it as epsilon sub t equals 2 is equal to x sub t is equal to 2 minus mu minus phi times epsilon sub t minus 1. Now take a look at this. That is exactly the same as we had written earlier. So for every time step where x sub t is not equal to 1, it's basically 2 onwards, we have it such that x sub t minus mu minus phi times epsilon sub t minus 1 is equal to epsilon sub t. So I can just replace this with epsilon sub t, because it's the same thing. We've just proven mathematically it's the same thing. And so then my distribution function can simplify to this. It can just be 1 over our square root of 2 pi times the variance, that doesn't change, times the exponent of, and I'm going to put square brackets here, minus epsilon sub t squared, because the squared doesn't go away, just that inner part did, over 2 times the variance. So we just shortened that formula dramatically. And for now, I'll just call that our function of x sub t given epsilon sub t dependent upon, some parameters. And there we go. We have our distribution function here that will work with fitting a moving average 1 model. Our likelihood function, which would be the likelihood with a bunch of parameters, is just going to be equal to big pi, so the iterative multiplication of this for each of our data points, starting from, t equals 1 all the way up to big T for every single x sub t. And remember, we didn't actually want to work with multiplication. We wanted to work with sum and sigma. So the way we can go from this multiplication version to summing all these data points is simply by using the logarithm of that likelihood function. So that would then change this pi to being a sigma, and then that would be, of course, sigma times the logarithm of this function here that we had written above. I'll probably do a YouTube short to show you how to get from the standard function to the log function version. It's basically just the logarithm of the likelihood function given our parameters is equal to minus big T over 2 times the logarithm of 2 pi minus big T over 2 times the logarithm of the variance minus sigma epsilon sub t squared over 2 times the variance. And we were able to get there just using the basic rules we have around sigma notation, but also working with logarithms. So for those of you who are really into your math, try and see if you can get from the formula we had earlier to this one. And for those of you who are just interested to see how we did it, I'll probably do a YouTube short on that for you. Great, so let's actually walk through this formula together now, but in Excel, and build it so that you can see what's going on. So first of all, this sigma of the epsilon sub t squared over 2 times the variance, you can see here, this is what we need to sum up for each data point because it's as of time t. The other parts of this formula are fixed. They're just the same value. They're not going to change. We don't need them in the sum. So I'm going to need in a column the areas that are affected by the sum. So I'm going to put that over here. And I'm just going to call this likelihood S, or I could call it something like sigma L or whatever you want to call it. I like something like likelihood for sigma. And that's just going to be equal to epsilon squared. So epsilon squared like that, divided by, and that's going to be 2 times the variance over here. Not the standard deviation, the variance. There we go. So that is our number over here. And we can just drop that down. And so that takes care of the first part of that formula. Now, we need to work out this other part, which is the t over 2 and all of that stuff. So let me just move this down a second. So here we're going to make big T equal to the count of all of these data points here. So count of all of those. And there you go. 403 data points. And then I need my t over 2 times the logarithm of 2 pi. So this here is going to be, and that's actually a minus, so it's going to be minus t over 2, and that's multiplied by the logarithm of 2 pi. That's what that there is representing. And I'm just going to put an apostrophe here so it doesn't think that's a formula. And so that's going to be equal to minus t divided by 2 times the logarithm of 2 times pi. Remember, this part here is fixed, so I don't need it in this sum here. Even though it's part of the same formula, I'm extracting it outside of this sigma over here, this sum that we handled on that column. Right, now let's just keep that formatting the same and give that some decimal places. And then I'm going to copy this down. And instead of this being logarithm times 2 pi, this is now going to be the logarithm times the variance here. So here I'm just going to put s squared for this to represent the variance. And let's get rid of that I over there. So that is going to be equals minus t divided by 2 times the logarithm of the variance down here. Great. Now we can bring this all back up and write our full log likelihood function, which is going to be equal to minus t over 2 times the logarithm of 2 pi minus there. So I'm going to add, because we've already minus this over here, I'm going to add that to it there, minus the sum of our sigma function here, which is all of those. And I'm just going to fix those columns over there. So let me just check I've got that correct. This is minus. Yeah, I've got the minus sign in there. I've got the minus sign in there. So I'm adding those two minuses together, plus another minus of this whole sum here. And there we go. This is the log likelihood number that we actually want to maximize. Okay, so this is a number here that we want it to be as high as possible. So let me just show you manually very quickly. Let's say I put mu to 0. You can see that's already made a big change. That number has already just shot up. And I'm going to put this here to something like negative 0.2. Or you can see it's gone up even more. If I put that to, say, a number like 1, you can see it went down dramatically. So it knows. We know roughly where we've got to put these numbers. Wouldn't it be great if we had a way to go and automatically have these worked out? My variance here, I want that to be greater than 0. That should be greater than 0. And then these two numbers here, I really just think, let's come up with something sensible, right? Plus or minus 10. 10 is a huge number in this context. We say here, this can go from minus 10 to plus 10, something like that. And the same with this one over here. And so in Excel, if you go to data, and here I'm using a Mac, here it's called Solver. Might be called something different on Windows, I don't know. Probably not. Probably it's the same thing, who knows. It says here, what do you want to set as an objective? So I want to set this log likelihood here as my objective. And it says, what do you want to do to it? I want to maximize it. I want this number to be as high as possible. It says, okay, well, what cells can I change in order to make that happen? So I highlight these cells here. These are the ones you can change. You can't change any other cells, only these ones. And then it says, okay, what constraints do you want to put on this model? So the first one I'm going to add here, I'm just going to bring this over here. It says, what cell reference? So this cell here, I want this to be less than or equal to, say, 10 at a maximum. And I'm going to add another one as well. Sorry, this is popping up on my other screen here. You can't see it. So this here also needs to be greater than or equal to minus 10. So same thing. And then I'm just going to keep doing the same thing. You should see here I've got these constraints now set up. So I'm going to add another one. And then it's going to be this one here. I want this to be less than or equal to 10. And I found, by the way, I'm doing the same thing again as the previous cell. But I have found, by the way, if you don't set parameters, and you can see how this works for you. If you don't set these, then it can go a bit haywire. It can go a bit funny. But anyway, so I'm going to add those in. And then final one, this one here, I want this variance. It can't be 0. It can't have a variance of 0. That shouldn't be possible. The model will break. So here we need that to be greater than or equal to, I'm just going to put some tiny number over here, some really, really small number. Okay, brilliant. So now that I've got these entered in, here they are. Here's all my constraints here entered in. I need to now decide what algorithm I want to use. And here I'm going to use this GRG nonlinear. There's other ones here you can use as well. These are different optimization algorithms you can use. And it says make unconstrained variables non-negative. So yeah, I just leave that checked. And here I'm going to say solve. My screen is frozen. This should happen to you as well. You can see the numbers are actually changing in front of us right now. And here it's saying, okay, we've managed to come up with a number. I'm going to say, okay, let's have a look. And you can see my log likelihood number has shot right up to 319. Let me just break these decimals out so that you can see this in more detail. So it's saying here that phi, it's come up with 0.512, mu is 0.001, and the variance is 0.012. And that was all done using maximum likelihood estimation on an MA1 model. So we have now figured out what the parameters are for this data. We haven't gone into testing for significance and how realistic is that number yet. Again, I'm going to save that. We're going to come to that in a later video. We've got enough to get our heads through right now. But this is the answer. This is the best this model can come up with using the GRG nonlinear optimization algorithm that we used in Excel. I believe that in Python, SciPy, is it SciPy or is it sklearn? One of the two has a minimize function in a library where you can actually give it what function you want it to minimize, and it will go and do that. Here we're maximizing it, but if I made this a negative number, so negative, and then the log likelihood function we've written here, I could minimize that negative. It's the same thing as maximizing the positive. It'll get me to the same result in terms of these parameters. So that's something to bear in mind as well. Now you might be wondering, why does this even work? Like literally, why does it work? How does this optimizer work? It's using calculus. So it knows it's working with curves. Remember, when you're dealing with probability densities or distributions, you're working with curves. And calculus is really good at finding the points on curves that are flat. In other words, here where we're trying to get the top of the curve, we're trying to maximize this number to the highest number possible by changing these. There's a computational numerical method to actually doing that. There's various ones of them. And then that's what it's doing. It's actually finding, where this gradient, where this curve doesn't need to increase anymore. But anyway, I don't want to make this about optimization because it really deserves its own video and I'm doing it no justice here. Now let's see very quickly, how would this look, just out of curiosity, if I used OLS to try to forecast the parameters here. So here I've got my dependent variable, which we've done before. So that's that column. And then the column here of the independent variable, right? So that's going to be E sub t minus 1. Let's just have a look. Very, very curious. How would that look? And so here I'm going to say we need to put a constant in and I don't need the stats. And there you go. It's saying here that this would be negative 0.568. So it's actually not far off. It's not a million miles away from what MLE found. This number is incorrect. Okay, it's not negative 0.568. And I have seen this go wildly wrong. In fact, here is an AR1 model that I've just sneakily prepared earlier, just to show you, because we've done this before. We know we can use OLS for this. I've actually put together some MLE, maximum likelihood estimation, for AR1. And this time we're using mu and beta rather than phi, because we're using the other function or math notation that we used earlier. Here is my log likelihood calculation. And this is all done slightly differently. I've had to set this up differently to work for an AR1 model. But here we go. So we've got this set up. Let's run our OLS on this. So here I can put linear estimator. We know these are our known y's. And I know these here are my known yt minus 1. Sorry, this could also say x sub t. I'll change that in a minute. And then here we go. We want a constant and no stats. And there you go. 0.477. You notice here I get to exactly the same numbers. And that's because MLE will give you the same results as OLS when we are not violating the rules for OLS like we were for the MA1. This here has worked. You can see this is correct. And this is also correct. Let's change this here just in line with this video to xt so you're not confused. But there we go. This here is my likelihood sigma. And here I'm going to call this the same over here. And this here is my MA1. Perfect. So now how do I do this for an ARMA? Well, let's just move a copy. Let's create a copy of this. this MA1. And now because I'm dealing with an AR as well, I've got my X hat over there, but actually what I really need to do is move this across here. And I need this to be X sub T minus 1. Because this here, let's face it, this here is X sub T. And this here is X sub T minus 1. In other words, it's these numbers over there. Okay, so here's my AR part in all of this. And I can't use OLS here because I'm mixing this in with data that's going to violate the terms of using OLS that we described earlier. So here I need to use MLE. And here's my error. So it's going to be X hat minus what X actually was, except here we need to add in another function here. So I'm going to bring this down over there. We've got phi, but we also need a term for beta because this is going to be for the AR version of the model. In fact, I'll make that beta and that phi. So let's actually calculate X hat here. That's just going to be mu plus beta times X sub T minus 1 plus phi times epsilon sub T minus 1. And then it would be plus the error term, but here we're getting the estimate. So this is X hat. We don't include the error term here. And there we go. This here is my X hat. So you can see I'm taking this number plus that number beta times X sub T minus 1 plus phi times the prior market shock. Let's drop that down over here. So here's my X hat. And then here's my actual error term. And I can leave this formula exactly the same. And I'm also going to add one to say that this cell should be greater than or equal to minus 10. And then let's go and hit solve and watch it go to work. Okay, so everything's frozen again on my screen. And there you go. It's running. And let's see if it can get to an answer. Here are the results. So we've got the same mu constant. Phi has changed. So it's gone from, what was it before? Here we had it at negative 0.512. It's now negative 0.339 because we're now taking into account another data point into our model of modeling relationships. And so here we have negative 0.227. And then here, again, a very small variance to take into consideration. So here we have modeled these parameters of our ARMA, so ARMA 1,1 model. This has been a lot to take in, but just to recap, what we've done here is fitted. In fact, we'll talk about it in the context of an AMA model. We have fitted a likelihood, a probability likelihood density curve to our data here. And we wanted to change some parameters that make up the result of that, such that the result of that gives us a number when we look at it, the probability of all of those data points happening, the likelihood, I should say, of all of those data points happening. When we look at the likelihood of all of those data points happening and we sum that up to one number, we get this number here. And if we maximize that one number, then we know we've got the optimum parameters for this. Again, I know that was a lot, but I do just want to say here that ARMA models, they're useful to a degree, but maximum likelihood estimation is useful for a lot of stuff. And so this is a great way to get into maximum likelihood estimation. So just get used to the concepts of writing the math notation. So what is it we want to model? What do we want to find the relationships between? Something is made up of a proportion of something else plus some error, plus the intercept. Remember our mu or alpha that we discussed in previous videos. That's one. But then how do you actually estimate those parameters? That's question number 2. And you can use different techniques. You can use OLS, or in this case, we had to use MLE because of the rules that we've laid out from before. And that will give us the answer. But really, we're still just estimating some fixed parameter. And when it comes to working with financial time series, it's actually unlikely that it's always just going to follow that one rule. That one rule can change over time. If it didn't, well, co-integration and trading would make a lot more money. Right? It would be, everyone would just do that one thing, and probably it would stop making money after that. But that's the point, is that it changes, market dynamics change, and something that's very useful to model that, or can be very useful to model that, are things like Kalman filters, which follow what's known as a state space model. So we'll get more into that stuff later on. This is enough to get your head around for now. Congratulations for making it through this video. I hope I did the topic justice, and I'll see you in the next one.